So next we come to crystal field stabilization energy. Now crystal field stabilization energy is something you can calculate and something which helps you predict how stable the complex is going to be, and that stability, that is the crystal field stabilization energy, it depends upon the crystal field energy or your delta. So the delta is the main factor on which our stability depends. So we will see how we can calculate the crystal field stabilization energy, but one of the main things for crystal field stabilization energy calculation is that it only has to be calculated for the excited state or for the non-degenerate state. It cannot be calculated for your degenerate state. This is your d orbital. So this is your d orbital in the ground state. All of the 5 d orbitals are degenerate, that is they have the same energy. Then they got excited a little bit, but they are still at the same energy. Now they got excited and they got not degenerate, that is now they are no longer degenerate. They have split. So the crystal field stabilization energy, they can be calculated only for this configuration, that is only for the electrons present in these two, that is the Eg and the T2G. It cannot be calculated for this, it cannot be calculated for this. Now let us see what will be the formula and how to calculate the crystal field stabilization energy. Now first of all, higher the CFSE, more stable will be the complex. So if a complex has higher CFSE, it will be more stable than a complex which has a lower CFSE. This is the formula for calculation of the crystal field stabilization energy in octahedral complexes. In this case, it is CFSE is equal to minus 2 by 5 del O into NT2G plus 3 by 5 del O into NEG plus delta NP into P. Here NT2G is the number of electrons in T2G, NEG is the number of electrons in EG, P is the pairing energy, and your delta NP. Delta NP is the difference of paired electron between split and unsplit configurations. So how to find out delta P, that will be more clear if we actually do the configurations and we calculate the CFSE. So that we will see in those in which actually delta NP is applicable. So let us calculate the crystal field stabilization energy for the octahedral complex which has D1 configuration. So D1 means there is 1 electron in D. So 1 electron, now that electron has gotten excited, and after excitation it has come to T2G, because obviously it is not going to prefer going into EG because EG lies at a higher energy. So it is going to prefer coming to T2G. So now that it has come to T2G, we can calculate the CFSE, because I told you CFSE can be only calculated for this configuration, that is this part. So CFSE is equal to minus 2 by 5 del O into NT2G. So NT2G here is 1. NEG, there is no electrons at all, so NEG is 0. And delta NP. Delta NP depends upon the difference in the number of paired electrons between the split and unsplit configurations. So there is no paired electrons at all, there is only 1 electron, and that is also half paired. So it is not paired at all, so delta NP is going to be 0 also. So if we substitute all of these values, our CFSE will come equal to minus 2 by 5 del O into 1, which is equal to minus 2 by 5 del O, which is equal to minus 0.4 del O. So the CFSE of the octahedral complexes of the D1 configuration is minus 0.4 del O. Similarly, we can find for D2 also. as well as D3. So D2 also the same thing. Now let's go to D3. In case of D3, there are 3 electrons here. These 3 electrons, they have jumped up. Now these 3 electrons have jumped up, they are going to come to T2G. So T2G is now fully filled. So I can say that N T2G is equal to 3. There are still no electrons in EG, so NEG is equal to 0. And still there are no paired electrons. All of the electrons are half filled, right? All of the orbitals are half filled. So there is no pairing of electrons at all. So delta NP is equal to 0. If we now substitute our values in the formula for CFSE, we will get CFSE is equal to minus 2 by 5 del O into 3, which is equal to minus 6 by 5 del O, which is equal to minus 1.2 del O. So the CFSE of the D3 configuration is equal to minus 1.2 del O. Now let's go on to calculate the CFSE of your D4 configuration. So D4 can be of two types now. As I told you, D1, D2 and D3, they are not affected by your weak field ligands and strong field ligands. They are not going to get paired anyway. So the high spin concept and the low spin complex concept cannot be applied to D1, D2, D3. It can be applied to D4, D5, D6 and D7. So for D4, D5, D6 and D7, you have to calculate the CFSE under different conditions. CFSE when it is a high spin complex and CFSE when it is a low spin complex. So first of all, for D4, we are going to determine the CFSE when it's a high spin complex. High spin complex means no pairing. So if there is no pairing, then 1, 2, 3 and 4, because high spin means no pairing, so I cannot put this electron in T2G because that will cause pairing. Now N T2G is equal to 3 and EG is equal to 1. Delta NP is still equal to 0 because again there are no paired electrons. So now if we fill these or substitute these numbers into our formula, we get CFSE will be equal to minus 2 by 5 del O into 3 plus 3 by 5 del O into 1. So that's minus 6 by 5 del O plus 3 by 5 del O, which gives you equal to minus 0.6 del O. So the D4 high spin is minus 0.6 del O. Now in this case, one of the questions that could be asked is why is 2 by 5 del O written in minus and 3 by 5 del O written in plus? It's a simple answer. 2 by 5 del O is in minus and 3 by 5 is in plus because 2 by 5 is getting lowered in energy. The T2G orbitals are getting lowered in energy, that is why we are writing minus 2 by 5. The EG orbitals are getting increased in energy, so it is plus 3.3 by 5. So this is the D4 high spin, which is minus 0.6 del O.